All right, in this lesson, we're going to look at the graphs of logarithmic functions. So because they are inverses of exponentials, we're going to go review the characteristics of exponential graphs and then see how those show up on a log graph. And because they're inverses, we just switch the x and y, so we'll have those relationships between them. All right, so you'll see here we have an exponential function graphed in this top graph where b is greater than 1 because it's increasing. So down here where it says increasing, I'm going to say it's because when b is greater than 1. In this case, this is actually a b is equal to 2. If you look at it, we have a y-intercept of 0, 1. We have no x-intercepts because there's a horizontal asymptote at y equals 0. All right, if we look at how those would, asymptote, I guess we list down here. It's horizontal, y equals 0. If I look at how those are different on the log graph, well, if we switch x and y, this 0, 1 would go to 1, 0, so we would have an x-intercept. 1, 2 would go to 2, 1. It's going to look something like this, and it's going to come down here. For a log graph, we have a vertical asymptote at x equals 0. So that means there would be no y-intercept. So see how those switch with one another. But if you notice, this is also an increasing log function. So this is your log function. The other one there is your exponential. When b is greater than 1, it's still increasing. Okay, so that's still true. All right, for decreasing, that would be the second graph when b is between 0 and 1. And let's look at what the log graph would look like. So again, we have that 1, 0 because it was 0, 1 on there. Then we have the point -1, 2. So I'll go 2, -1. This is going to look, so this is your log. The other one is your exponential. Again, same base between 0 and 1 makes it decreasing. So that's a nice similarity between them. For both of them, your exponential has a domain of all real numbers. So that means the log has a range of all real numbers. For our exponential, the range is stopped at 0 or starts at 0 because of the horizontal asymptote. So the range is anything greater than 0. And then because we have a vertical asymptote for the log functions, that's why the domain is just greater than 0. All right, so there are a lot of similarities between them. So things that if you can remember about the exponential, because you're usually a little bit more familiar with them and comfortable, then you just have to switch your domain and range, your x and y, and you'll know all your facts about your log functions. All right, so just a little recap, your key characteristics. So a log function, this is the general form. B has to be greater than 0, just like your exponentials. F of x equals a log base b of x, okay, where a isn't 0 and b isn't 1. The domain is anything greater than 0 because of the vertical asymptote at x equals 0. And then the range is all real numbers. All right, what they look like if you have base is greater than 1 and a is greater than 0, looks like a nice increasing log function. All right, and on the other one, if your b is greater than, that shouldn't be, it should be b is between 0 and 1. And it looks like this here. Oh, I guess if a was, okay, that reflected it. So I guess we could do either one. It would be either what they said. So sorry. If a was less than 0, that means it's a reflection. Or If A is greater than 1 and B is between 0 and 1, it would look similar to that. It would be that decreasing function like we saw back here. Logs are always increasing or decreasing. There's no change in concavity. There's no change. There's no relative extrema. Okay, so they're always concave up or concave down. All right, so they're always increasing or decreasing. No relative extrema. Always concave up or always concave down. No points of inflection. Very similar to your exponentials. All right, your end behavior. These you will have as x increases without bound. The outputs will increase or decrease without bound. We also have to pay attention to the left end behavior, that as x goes to 0 from the right, that's what this means. As x goes to 0 from the right, that's what that little plus sign up there means. Because there's a vertical asymptote, so we can only approach it from one side. Then you have to pay attention to the vertical asymptote and how we approach it going up or down. All right, and then your behavior limit statements would look like those. We're going to go to infinity or negative infinity, and this is approaching 0 from the right, and as x goes to infinity. All right, so let's write some limit statements here. So if we're looking at this graph, the limit as x approaches 0 from the right, so that means as we get closer and closer from the right, this is infinitely decreasing, so going to negative infinity. And the limit as x goes to infinity for f of x, that's increasing without bound, so going to infinity. All right, for this middle graph, again, so from the left, we're talking about as we approach 0 from the right, we're going to be infinitely larger, so infinity. And then the limit as x approaches infinity for h of x, it's going to negative infinity. All right, now the last one, it would help to make a little sketch of it. So we know that there is that point, and if it's 3, it's going to be an increasing function. So the limit as x approaches 0 for g of x. From the right, that's going down forever. And the limit as x approaches infinity, that's getting infinitely larger. All right, so let's see how transformations impact our log functions. So you'll notice in all of these, we are graphing, because we got the 0.01 and then the 0.21, then it looks like 4.2, so it looks like log base 2 of x. So if we have any, let's talk horizontal translations. Horizontal, remember, always impact the x, so that's where it would be x plus and minus some value there. Okay, that shifts it left and right. Okay, so if we add or subtract, we're moving this whole function to the left or the right. If we have vertical, you would see them outside of your log, plus or minus. We'll call that k. Moving it up and down, okay? Horizontal dilations, that again has to be in on the x, so it would be something multiplied right to the x. Remember that the factor would be 1 over b. And then if we've got vertical, that would be out in front. And I guess these should all be 2, shouldn't they? I don't need to use an a there. Oops. But I'm using a. You would have something out in front. I'm just going to put the b out here. And that would be a factor of b. All right, and then reflections. So a horizontal reflection means that we are reflecting over the y-axis. So gating. And then if it's vertical, you'd have the negative out in front, and that's over the x-axis. So which transformations are going to impact the domain and range? Well, let's go back up here and look. If we add or subtract and go left or right, let's say I went left or right, 3. That would move that vertical asymptote and it would impact the domain. So for domain, that would be horizontal shift. Okay, it moves that vertical asymptote, so your domain is impacted. If we shift it up or down, that is not going to change your domain, and it won't change your range because your range is all real numbers. And it's still going to be all real numbers. Okay, let's look at horizontal or vertical dilations. So let's say we did a scale factor of 2. So it would just stretch it horizontally, not going to change that where that asymptote is, unless there's a horizontal shift. So the horizontal shift is key. All right, and if we do a vertical dilation, not going to change your range again because it was all real numbers. So the range isn't going to change. All right, now if we have horizontal or vertical reflections, if we reflect over the y-axis, we're going to approach 0 from the left-hand side, so that will change the domain. If we reflect over the x-axis, it's just going to look like that, still have the range of all real numbers, so not change it. All right, so now we're going to decide if we are increasing or decreasing and the concavity. So if we look at this function, as x increases, y is decreasing, and it's concave. Oh, not down, concave up the whole time. On the next one, this is concave down, but we are increasing as we move along it. All right, last one's a little tricky, so we got to figure out what this looks like. Originally, with this base, it would be an increasing function. But then, with that reflection, it's now going to be a decreasing function and concave up. Okay, so here we're given that we have values from a log function. We need to find k, so k is some kind of missing number in here. When we look at our tables, we want to notice that we have equally spaced y values, and we want to figure out what that factor is that we're multiplying by, okay, our proportional scale factor in the x's. If we look from 1 to 2, looks like we're multiplying by 2. If we look again from 8 to 16, multiplying by 2. So in this case, k would have to be 2 times 2, which is 4, and then 4 times 2 would get you 8. Okay, so all have equal length output intervals, and the inputs change proportionally. So we're looking for what that proportional scale factor is and then applying it. All right, if we look again, equally spaced y intervals. In the x's, if we go from 6 to 18, we're multiplying by 3. 18 to 54, multiplying by 3. So if we go backwards, we'd have to divide 6 by 3. K would be 2. In the last table, a little trickier maybe. Equally spaced output intervals. So think about this. We're multiplying. And since these are all base E, when we multiply bases that are the same, you would add exponents. So when you go from -2 to 1, we multiplied by e to the third, because that's what you would add to -2 to get 1. Similarly here, we're multiplying by e to the third to go from e to the 7th to e to the 10th. So to get k, we'd have to do e times e to the third, which would be e to the 4th, which then makes sense because if I do e to the 4th times e to the third, I'd end up with e to the 7th. All right, figuring out our domain and range. So when we look at our functions, remember, what impacts our domain are those horizontal shifts and the y and the reflections in the y-axis. All right, it's going to be anything that's inside your log associated with that x. So in each case of these, anything in there is what impacts the domain. And remember, because of that vertical asymptote, that quantity has to stay greater than 0. So for this first one, our domain would strictly be anything that's greater than 0. Your range, all real numbers. That's going to be the case across the board. The range is all real numbers. The domain, though, keeps changing. In the second one, you would take that quantity, x minus 3, set it greater than 0, solve that. Now this means that our whole graph shifted to the right 3, so our vertical asymptote is now at x equals 3, so our domain is anything greater than 3. And on that last one, we've got a shift to the left 3 and a horizontal dilation. Okay, so if you have a shift, the dilation also then impacts your domain. So if I set that whole quantity greater than 0 and solve it, x is greater than -3/2. All right, so finding that domain, set the quantity you're taking in the log of greater than 0, and that's what you'll find it to be. All right, and one last one. We're going to make a nice little graph and answer all the questions. So I would kind of graph as we kind of talk about it here. Range is easy, all real numbers. Domain, because we're shifting this to the left 3, we'd have a vertical asymptote at x equals -3. And our domain would be anything greater than -3. Okay, because that would be taking the x plus 3, setting it greater than 0, and solving. Now, since it was a base 2, that means it would be an increasing function, but then we have the reflection over the x-axis, so it's actually going to be a decreasing function. So when we talk about our end behavior, we're going to do the limit as x approaches where that asymptote is, so -3 from the right. And we're going to talk about as x goes to infinity. As it goes towards -3 from the right, that increases without bound. And as x goes to infinity, it decreases without bound. Okay, so we should have an understanding of what the transformations, how they impact our graphs. And oh my goodness, I did not see this at all. It would shift it down, not changing our domain or range or anything, but it would shift it down. Totally missed that on the function. Not going to change any of the end behavior, but it would just move it down there.